the basic units of measurement, accuracy, precision, and significant figures, use of Fahrenheit, Celsius, problem solving, unit conversion, dimensional analysis, density, kinetic molecular theory, gas pressure, Boyle's law, Charles' law, Dalton's atomic theory. Okay, up to this point is chapter 4. And then Dalton's theory is chapter 5. We talked about Dalton's theory. Atomic structure, the nuclear atom model, chapter 5. Okay, that will be on the test. Identifying elements. Let's see. Identifying Identifying elements, have you guys worked through that one? Not yet. Nomenclature? Nomenclature is chapter 6. So let's go to my dashboard here. Take a look at this. We didn't get ions. Ions in chapter 6. This is chapter 6. Chapter 6. Calculating atomic mass. This is chapter 5. Identifying ions and isotopes. Let's see what this one is. It looks like actually. Ions and isotopes is more chapter. It's kind of tricky because isotopes is chapter 5 and for us, but chapter should be mixed with ions. And so you should get through part of this, probably up through this is gas, Dalton's atomic structure, identifying elements. Probably stop here. Ions and isotopes. So that's it. Okay.
You said the last chapter was chapter 8.
The last part of chapter 5. Last couple of parts of chapter 5. We did the Rutherford, right, already yesterday? Rutherford model? Rutherford gold scattering experiment yesterday? All right. So this is kind of review still. We talked about subatomic particles already. We talked about isotopes, right? Hydrogen, etc. Nuclear symbol. We did this, correct? This is where we stopped yesterday. So let's go ahead and finish this chart, and then we'll finish up chapter 5 with this. All right, which one? Where did we stop yesterday? We did oxygen. Finish it. All right. So now we're doing this. We're doing atomic number 82. Atomic number 82 is element number 82. What is element number 82? Lead. And so LEAD is the name. The symbol is PB. How many protons does lead have? 82, because it's going to dictate the properties. So 82 protons is lead. How many neutrons? Well, in order to know the number of neutrons, we have to know what isotope of lead we're dealing with. And the isotope of lead that we're dealing with is lead 206. And So 206 minus 82 would give us the number of neutrons. What is it going to be? 24. Okay, so we have 24 neutrons.
124.
124 neutrons. Yeah, 124 plus 82. That's right. The nuclear symbol. The nuclear symbol, I'll give you two options for the nuclear symbol. We don't really need to write the 82 because lead is element number 82. And so this 82 is often left off. But in this case, they're writing it down here. This is our Z. But we have to have our A. Our A is going to be 206. Is that an exact number or approximate number, 206? That's exact because that's the number of protons plus the number of neutrons. Is that the mass? No, it's not the mass, but it's close to it because protons and neutrons weigh about 1 U, and therefore this atom will weigh about 206 U. All right, let's go on to the last row here. This is zinc 66. And so maybe we'll go to the nuclear symbol. What's the nuclear symbol for zinc 66? Does the 66 go on the bottom or on the top? The top. What goes on the bottom here? The atomic number of zinc is? You see it? 30? The name of the element, ZiC, zinc. The elemental symbol, Zn. Atomic number, 30. Number of protons, 30. Number of neutrons, 36. Mass number, 66. We did the symbol. So this will be the way we represent the composition of the atom. Now, when we're dealing with atoms, we deal with it from two perspectives. This is unnecessary. The two perspectives that we deal with atoms are if we're dealing at the particulate level versus at the macroscopic level. And so there are going to be like two types of chemists out there. Broadly speaking, two types of chemists. Okay, one type of chemist works at the particulate level. Particulate. A person working at the particulate level is looking at single atoms and single molecules. And so, for example, water, if you were to take one water molecule out of a cup of water, then you have to worry about it because how many different water molecules are there in a cup of water? It turns out that there are 9 of them. Can you list them? So if you were to take a single molecule out of a cup of water, you might have taken this molecule, the most common one. This molecule, more than 99% of the water is this. But you might have also taken one of these molecules. This is the next most abundant water molecule, in which you have one hydrogen 1 and one hydrogen 2, which is a deuterium. Or you might have taken this water molecule, which is a deuterium, oxygen 16, and a deuterium. There's probably no tritium in your water, so we're going to skip the tritium. Otherwise, there'd be even more choices. But the thing about oxygen is oxygen 16 is the most common. But do you know what the other isotopes of oxygen are? The other isotopes of oxygen, this is the field that nuclear chemists are concerned about. Nuclear chemists want to understand the structure and the properties and the composition of the nucleus. That way they can predict how many isotopes, what their relative abundance will be, et cetera, et cetera. And so when we look at oxygen, How many isotopes of oxygen are there? Well, what we'll do is we'll just do an experimental measurement and figure it out. There's oxygen 16, which is 99.757% of all oxygen atoms. There's oxygen 17, which is only 0.038. Can you have 0.038 parts of an atom? No, so what we would do is we'd move the decimal 3 over. And so if I have 100,000 oxygens, 99,757 would be oxygen 16. If I had 100,000 oxygens, only 38 would be oxygen 17. And out of that 100,000, I'd have 205 that are oxygen 18. And so the most common is oxygen 16, followed by oxygen 18. But I'm going to go 16, 17, and 18 to keep it in order. And so I might have picked out a hydrogen 1 with an oxygen 17 to a hydrogen 1. What are the others? A hydrogen 1 to an oxygen 17 to a hydrogen 2. A hydrogen 2 to an oxygen 17 to a hydrogen 2. Or I might have picked out a hydrogen 1 to an oxygen 18 to a hydrogen 1. A hydrogen 1 to an oxygen 18 to a hydrogen 2. Or a hydrogen 2 to an oxygen 18 to a hydrogen 2. Now, could you tell the difference between those water molecules when you took a sip of water? No, you can't. And chemically, are those water molecules going to behave differently? No, they aren't. Chemically, they're going to behave similarly. The difference, though, will be in how much they weigh. And so, this one's going to weigh about how many? U, roughly. Well, how much does a hydrogen atom weigh, roughly? 1 U. We have 2 of them, so there's going to be 2. And then how much does an oxygen 16 weigh? Oxygen 16 consists of 8 protons, 8 neutrons. 8 protons is 8 U, 8 neutrons is 8 U. The electrons are about 2,000 times lighter, so we can kind of ignore the electrons. And so it should weigh about 16 U. And so this whole molecule is going to weigh about 18 U. This molecule will weigh about 19 U. This one, 20. This one, 17 plus 1 plus 1, 19. This one, 20. This one, 21. This one, 20. This one, 21 U. This one, 22 U. And so the heaviest one weighs 22 U, the lightest one's 18 U, and then we have these in between. So if you're dealing with individual molecules or individual atoms, you are very concerned about which one you get. And so that's at the particular level. So the same thing happens if you have a sample of carbon. If we have a sample of carbon, then at the particular level, we got to concern ourselves. A carbon in graphite form, and I'll just spread out the atoms so we can see it, forms these hexagonal sheets like this. Most of the carbon atoms are what? So we look up at the data. Most of the carbon atoms in graphite are carbon 12. And how much do carbon 12 atoms weigh? Exactly 12 U by definition. And then once in a while we'll hit a carbon 13. And so the way you would read this is like this. The way I'd read this is for every 10,000 carbon atoms, 9,893 will be carbon 12 and 107 will be carbon 13. And so once in a while, we'll hit a carbon 13. And so we'll black it out like this. And so it depends. If you're working with single atoms, let's say we have a laser, we're vaporizing some atoms off the surface of graphite, then we care. Are we vaporizing a carbon 12 or are we vaporizing carbon 13 because they weigh different amounts, right? And so we want to keep track of the weights. But, if I have, let's say, a macroscopic quantity. Let's say I have 18 milliliters of water. In 18 milliliters of water, there are going to be 6022, 1, 2, 3, and then 10 zeros. Put in 1, 2, 3, 5, 6, 7, 8, 9, 10 zeros. And so let's figure out what that is. It's 1,000, it's a million, a billion. Actually, did I get this right? No, I didn't get this right. Let me redo this here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, another 10, 14, 15, 16, 17, 18, 19, 20, 21. And so that's 1,000. So it'll be a million, billion, trillion. What comes after a trillion? Well, actually, I don't know. So we'll stop there. This will be a trillion. And then what we'll do is we'll just add on top of that. This will be 1,000 trillion, a million trillion, a billion trillion. And so this is a billion trillion, 602 billion trillion. So if I have 18 milliliters of water, do you know I have 602 billion trillion water molecules? Could you count all of them? No, there's no way you're going to count all of them. And so are you going to be concerned about, some way more than others? No, you got so many. And since you're dealing with so many, then we don't really care about the individual. If you got so many, you stop caring about the individual and you just start caring about the average. And so the average, the average what? Well, we're going to be caring about the average mass. So this will be H2O molecules. The average H2O molecule, do you know how much it weighs? The average H2O molecule weighs 18.02 U. It's very close to 18, although that's not exactly 18 there. And that's because the average hydrogen, the average H atom weighs 1.01 U, and the average oxygen atom weighs 16.00 U, because it's primarily oxygen 16, which is dominant, and it's primarily hydrogen 1, which is dominant. And so we're interested in the average mass. In fact, we call this the average atomic mass, those values down there. The average atomic mass is just shortened to atomic mass. So when somebody's talking about the atomic mass, they're talking about the average weight of a carbon atom, average weight of a hydrogen atom, etc. If they're talking about isotopic mass, then they're looking at individual atoms of a specific isotope. And so we'll just say VS versus isotopic mass. Isotopic mass. All right, when we're dealing with averages, it's a tricky average because it's a weighted average. Normally when we take an average, it's like this. What's the average of 12 and 13? The average of 12 and 13 is 12.5, 12 and a half. But the problem is that's assuming it's a 50-50, that 12 and 13 are equal contributors. They aren't. In this case, there's a much more dominant contributor, and that would be the 12. And so the average mass is going to be much closer to 12 than it is to 13. And so there are two ways we do this. And so this is one more technique I want to bring up for problem solving. For problem solving, we have, sometimes we have two equations and two unknowns. So if we have two unknowns, we need two equations, right? And so two unknowns, the first way we can solve this is using two equations. The second way we can solve this is by graphical analysis. And so let me just show you graphical analysis for something like this. For graphical analysis, the way we visualize it is like this. We start off at 0% carbon 13. If we have 0% carbon 13, that means we must have what percentage carbon 12? 100%. I mean, this is a mixture of carbon 12 and carbon 13. And so if it's 0% carbon 13, we have 100% carbon 12. If it's 100% carbon 12, how much does it weigh? It's going to weigh 12 U. Okay, then what we're going to do is we're going to vary this. We're going to go from 0% carbon 13 to 100% carbon 13. If we go to 100% carbon 13, that means we have 0% carbon 12. How much does it weigh? If there's no carbon 12 and it's all carbon 13, then it's got to weigh 13 U. If it's 50-50, you know, if it's half 50% carbon 12 and 50% carbon 13, that places it right in the middle. How much does it weigh? It's going to weigh 12 and a half. And so what we see is we see this graphical representation of this relationship like this. Here. Now, what if it weighs, well, actually, let's not do the weight. What if it's 75% carbon 13? If this is 75% carbon 13, what's the average? If it's 75, okay, if it's 50% carbon 13, it's halfway. If it's 75% carbon 13, it's 3/4 of the way. 3/4 of the way will be 12.75. If it's 25% carbon 13, it's here. That means it's 75% carbon 12, which brings it closer to carbon 12, which means it's 12.25. You see that? Now what if it's 90%? If it's 90% carbon 12, what is its weight? Well, if it's 90% carbon 12, then that means it's 10% carbon 13, which means its mass will be 12.1. And so if it's 90% carbon 13, it's 12.1. What if it's 99.9% carbon 12? We out of time? If it's 99.9% carbon 12, then it's going to be 12.01. Well, you know what the average mass of carbon is? The average mass of carbon is 12.01, which means it's 99.9% carbon 12. And so we could get more precise numbers if we actually do the math for this, but this gives us a quick way to visually see what the number should be. And so we'll do some more mental calculations and some more quantitative calculations next time.